now to the Rolls-Royce of what we were taught. That's big words, a small Rolls-Royce. I don't know the details of Rolls-Royces, so I don't know what they are called and what the engines are. Anyway, here we start. 3 topics, 3 lectures. This one, I think you realized when I did this one I particularly like. Since even though I only give you tools, simulation-based statistics in a rather limited setting, I only give you some tools for doing simulation-based statistics for 1 and 2 sample data, looking at means. Like the slide that I showed a couple of slides ago, where I was summarizing what did we do in chapter 7 and 8. I could compute 1 mean or 2 mean. I could compare them by t-test, typically, back in that. Now we are giving an alternative, because those tests that I gave you in chapter 7 and 8 is only valid if either the sample size is big enough, and we say big enough is beyond 30, or if we may assume that the phenomenon that we are observing, the system we are observing, is really acting like a normal distribution in the first place. So the pattern of the raw system, the raw observation, the random probability system that could apply to individual observations should be a normal. And that's a rather restrictive assumption. So either we use it because the normal is valid from the beginning, or we use the normal and t because central limit theorem comes in play for a large n. But what if it's not normal and n is not large? What should we then do? Then we do statistics by simulation. That's the name of the game here. In that part, I did introduce simulation as a more general computation tool within probability, and it's a strong computational tool for all of us who are not probability theory experts, and I bet there are many of us out there. Even though we are not probability theoretical experts, so it's very difficult for us to deduce complex features of nonlinear random systems. That's extremely mathematical challenging. It's not always impossible. Sometimes it is impossible to do it exactly. I mean, you shouldn't put a very much of difficulty into a system. And difficulty comes, complexity of systems comes, the more realistic you want to make models. And the models I present to you are rather simplistic. We need to start simple. If we want to adapt those models that I present in my course to meet the real world more reasonably, then things become more complicated. And more complicated means more difficult to compute things. But then if we could just add in a little bit of program code in R, it's very easy to do the simulation part in R, and we could just look at the features coming out of R and learn from that. It's an extremely strong computational tool for all of us to be able to deal with simulations. And it is, the awareness of this has not, come across out there in industry, in society yet. I mean, many scientific people are using it, but there's still a way to go before it's used to the extent that it can really be used. So you can do it in the future. For statistics, we call it bootstrapping, what we do most of the time when we do simulations. So bootstrapping is one way of doing simulation stuff. This is a statistics thing we do, that when we have a sample, and we should be worried about the sample distribution, that's what I told you. The sampling distribution of whatever we compute, as I said in chapter 6, is the core to become intelligent. Then we use probability theory, usually, before this chapter. We use probability theory to find the sampling distribution, or we relied on what other people told us from otherwhere. I mean, we didn't prove the things in our course, we picked the results from out there to use in our course here. Now, we don't want to do that. We don't want to rely on theoretical results. Maybe, if we are worried that the basic assumptions are not valid, then we could do a million intelligent theoretical things. If the thing we put into all the mathematical derivations are wrong in the first place, because they don't match the real world, then all the advanced math become meaningless, because we're doing a lot of advanced math on something which is wrong, and we'll hit the wrong target, we'll hit off the target anyway. This is where we can do something better sometimes. We can resample, we can construct artificially many samples and look at what happens in a sample distribution. So we create our own sampling distribution by taking again and again samples out of our own sample. That's bootstrapping. I should mention that there are improved ways of using the bootstrap results compared to what I tell you. Again, this is a start course. So also the bootstrap approach can be extended to become even better than what I've told you. That's an important point. We could do also, this could provide confidence intervals for us. We simply resample, and then we see how it goes, and we read off the percentiles in the observed distribution. That's how it goes. We need R for this. We cannot do it by hand. I'll give you an example before the end of today how it may look in an exam exercise, because that could be interesting to know at this point. Then we can also do hypothesis test by simulation. We could do it either by basing the hypothesis test in simple cases on the bootstrap confidence intervals and say, hey, if the bootstrap confidence interval includes this, this is an acceptable value. If it doesn't include, it's not acceptable. In this way, we can do hypothesis testing by confidence intervals. Or we saw one other thing, that if we have, we only saw it in the two sample, the permutation test. We saw it in the two sample, but this is the permutation test was a way, an approach that more easily generalizes to more than two groups, actually. We saw that this was a slightly different way of resampling. Really, it was permuting things where we pooled the two group data together and sort of shuffled it around and split the data at random, and then we saw how it went. That is, in short, that's what we did. This was the simulation part, a really nice thing to remember in the future. The next to last part, the regression analysis, is also something that you inevitably will meet. I mean, basically everything you see in my course, you will meet out there in the future. I will be surprised. You can come back to me in 30 years, visit me on the old man's home, and complain if what I tell you is wrong. But I'm convinced that all of you, if you go out and if you get a job as a civil engineer, you will meet this. You cannot avoid it. It's part of being intelligent that you can look at numbers and learn from them and know the limitations of them. As a highly educated person, you must be able to do that. Medical doctors must do it, biologists must do it, civil engineers must do it. Economics people must do it. I can't even think, maybe if you are doing gardening, maybe gardening you don't have to do it. I think that's the only thing I can, maybe if you're a dancer also, or a singer. Anyway, you have to do it. I was about to drift off. I should try not to drift off too much here. The regression analysis, X and Y, two things we plot against each other. This is the very basic way we can look at two things at the same time. This is why this section is very basic. And how can you do that? You can plot them. I mean, we were taught that in 3rd grade. We can also put in a line, if we want, to summarize the story between X and Y. There is a principle of putting in such a line, which is called the least squares principle, in which we minimize this squared Y deviances to the line. So this is the least squares thing, that we take each Y and minimize its squared difference to the line position. So we find the line which is closest to the points, measured in a least squares way, which is the vertical distances in such as XY scatter plot. That's the least squares line. There could be different ways of putting in a line, but this is the most standard way of putting in a line. This is something that you could have met in other places. You could see that as just a mathematical task. That's a minimization problem in two variables. Find the slope, find the intercept. So you don't have to think stats necessarily to put in a line. This could be done, just say, I want to make a line. This is the principle, I want to make the line. So that's what I do. However, we are going to think stats. We are going to add the intelligent part of it, the thinking part of it. If the y's represent some population, it may not always, of course. If it's just something you make up or whatever, you may put in x and y's that you sort of don't sample at random from anything. And then, of course, you shouldn't do stats. But if you have sort of randomly sampled the observations, then we have this basic way of expressing mathematically that there is a line, and hopefully that's well known to us, the formula for the line, but we put it into a stats framework by this adding the epsilon I, that there is the individual y measurements are coming on average as a line depending on the x values, but then on top of that there is an individual epsilon, there is a difference to the line given for each, and that's the random part. It's the difference from the line which is random. The line is sort of the expected value, right? Then we can do confidence intervals and hypothesis testing for the intercept and the slope, and we can do confidence interval for the expected line, and we can do prediction interval. That's the three statistics things we were taught in the regression part. We can do, I repeat, statistics about intercept and slope individually, and usually it's the slope thing. This is the slope, which is the interesting part, because the slope really tells the story about how y depends on x. The intercept itself is very often just some artificial place where the line hits the 0 point. And the number itself is very, very often sort of meaningless, because the number is outside the range of data. So in that way, the intercept often is meaningless as a number in itself. It's just something to place the line where it should be, you could say. The interesting part is the slope, the beta. We can do statistics about those. We can combine those two, with the slope and intercept, to do statistics for the line. That is, if we want to say something about the expected line. I had the example, if I want to say something about the population, the average weight of those guys that are 180 centimeters tall. That's the height-weight example that I used when I did the lecture on this. If I'm having weight as the y and height as the x, I could use the line, if I made a line there, to estimate the average weight for guys that are 180 centimeters, right? That's the population average weight. That would then be a confidence interval I could apply there. Then I could use the line in a different way. I could use the line to predict one person's weight by getting an input x from this one person saying, my height is 180 centimeters. Would you be so kind to predict my weight using your model? Yes, I'll do that exactly as I used it before. I'll plug in the line, of course. I'll predict the weight, which will be the same as the estimate of the mean weight of those guys. But since now I'm predicting a single person's weight, there'll be some additional uncertainty in this prediction. So there is another prediction interval, which basically is the same as the confidence interval, with the one added in the formula, giving an additional standard deviation into the uncertainty there, into the confidence interval. Then finally we had some things about correlation and the squared correlation. Correlation was this measure of strength of linear relation between 0 and 1. The squared correlation was the coefficient of determination, also called the explained variation. The amount of y variation explained by x. That was the interpretation actually of the squared correlation, which is between 0 and 1. That was the regression part. Now to the final part, analysis of variance. So we not only have two samples, we have k samples. They could be either independent or they could be dependent. They could either be independent or they could be dependent. If they're independent, we learned about the one-way analysis of variance. It's a way to compare the means of those groups by constructing certain variabilities, actually. That's why it's called analysis of variance. We construct this SSTR, which is kind of a variability measure of mean differences. That you look at the different means of the groups and you see what is the variability of those group means, basically, because you compare them with the overall mean. And this sort of measure of group difference is called SSTR, and basically this is compared in the right way to the SSE, to the variability within groups, sort of the noise within groups. And if you sort of do it the right way, you get an F-test that you can compare, and you could do post hoc testing of specific group differences. Now we're getting tired. Final thing. The dependent part, which is the this is the extension of the two independent samples from chapter 7-8. This is the extension of the two paired samples, because if I have many samples, then you cannot call them paired, but then we call them blocked or dependent. It could be the same guy. We had the example with the same people coming in to 4 different listening tests when you're going to adjust the hearing aid. So it could be the same person coming in not only 2 times, but several times, like 4 times in my listening test example. Then we can extend the ANOVA thinking and both look at how different are the groups from each other and how different are the blocks or the people or whatever is the blocks. Blocks could be many different things. We could see the table in one way, we could see the table in another way. That's why it's now called two-way analysis of variance. The aim is still to compare the means of the groups. And we can do that as for the one-way by F-testing. In my examples, next lecture, next hour, I'm going to show you a bit of examples there. So let me stop here on that. That was the whole course in 3 by 12, 13 minutes. I'd like before the break to do the next second part, just a 5-7